Okay, we are recording now. So, good morning, everybody. So, today we're going to be talking about the build part of a pulse oximeter. So, um, as we talked about on the last several videos that I've released, I gave you kind of some of the mathematical theory behind, um, you know, both near infrared spectroscopy, which is kind of the more general sense where we use optodes in different areas of the body to try to measure what's going on inside, and its functional version. When we try to figure out how the brain is working, we'll put a whole array of them over. We talked about the mathematics of how we're going to extract a signal. Today we're going to build a circuit, and we're going to build a fairly simple circuit that's on. We're going to talk about a few varieties here, and then we will build one. I've got some equipment sitting over on my dryer over here. So let's start off with a little kind of introduction to the idea of the build. So we've got two basic different devices we're going to deal with. One of them is a light emitting diode. So a light emitting diode, whenever you run current through it, is going to emit light. Now, in truth, all diodes do this. There really is not, if you want to get down to it, there's not really truly a light emitting diode and a non light emitting diode. It depends on what frequency range, whether human beings can see it or not. And it also depends on whether or not there's an outer protective sheath on them. So you'll notice most PN junctions, right? And that's all a diode is, will have a covering on the outside of them. So, for instance, transistors, which have two PN junctions, actually have coatings on the outside of them. It's usually a black plastic layer. This isn't just for stylized, it is a little bit protective, but a lot of it is actually to prevent light from coming out of it. Um, Most transistors, like the standalone ones, actually will emit light that's at least partially visible to human beings. So if you were to gently grind off that outer coating and you were to operate them, you would see them kind of blinking and flickering and glowing um, as you're going through. The other part of this is pretty much every single one of our PN junctions also will do the opposite. It will receive light back in. You also have the opposite direction where photons coming in will actually bump electrons up, allowing there to be more electrons in that conduction zone and allowing current to flow. So photons, due to the photoelectric effect, can actually knock electrons out and therefore cause there to be a current running through the diode. It is the second effect that is going to become kind of crucial in the bigger part of our circuit. Now, if you want to increase this effect of receiving more photons, what you have to do is you have to make the PN junction larger. So I can optimize it for one of these or the other. For receiving, you want as big of a PN junction as you possibly can get. And this becomes a little bit of an issue because the larger your PN junction, the bigger the capacitance in your circuit. So the second you put a capacitor in, so you can kind of model a diode when it's conducting as if it is a capacitor, the resistor in series, right? And that resistor is usually fairly large, but the capacitor can cause all kinds of nasty things when you go to do amplification. It can create backlashes and lags and all other kinds of weird stuff in the circuit. And the bigger the capacitor, the worse this gets. So in order for this to work, we're going to have a fairly big receiver here on this photodiode. And that means that generally we're going to get more than we kind of bargained for in this sense, in that we're going to get, there'll be more noise and some other stuff. Now, I'm not going to sweat the noise too much because our signal is fairly strong. So this is not too bad for our application. But if you've got a very, very sensitive application, then it will matter quite a bit. So that's just kind of an important thing to remember on how these are built, that you need larger and larger areas for this at that PN junction, which means it has to get bigger and bigger, and the bigger it gets, the worse. So all right. So that's one thing. To optimize both ends of this, both the emission and the receiving for a particular frequency, there's two basic things you can do. You can adjust the materials that you dope with, and there's a couple different ways to do this. There are kind of the standard way is to adjust what the material is, and they have transmission bands, and so you can adjust the color of light by what materials you kind of dope into them. Um, that's kind of the original way. It wasn't the super high efficiency ones. We then discovered that you can get organic molecules that can fluoresce and then quantum dots. Um, but without getting too fine into that, I can adjust the material and structural properties of this to make it more efficient for a particular frequency of light. And whenever they tell you that you've got a particular thing, like for instance, you might buy, let's say, like a red LED that is, 660 nanometers. That does not mean that if you're looking at your frequency chart, they're right at 660, that you have like a spike. That'd be lovely, but it doesn't happen. What you actually have is that's kind of the peak frequency, and you've got this really big kind of sway. And the material choices you're trying to get it where it goes. Now, the human eye, as this gets larger in frequency, really cannot see past about that point. That's about your limit. Because this is red and you're heading towards blues and purple this way. Purple over here. So we're right on the edge of kind of human sight when we're traveling in here. So the infrared stuff is invisible to you. But to get rid of the other stuff, oftentimes the plastic coatings that's around them, we can actually put a material that will absorb certain frequencies we want. Now, in this case, we can actually even push some of the red ones over a bit. Since the human eye has some restrictions, we don't necessarily, red LEDs can actually have a lot of infrared that they're also emitting because the human eye doesn't see it, so who cares? Sometimes they will put an IR filter on them. The IR filters are completely invisible to us, so and then knock these off. And so that's the second way that you can handle it. So the first way is adjusting at the emission end by adjusting what materials are used to actually do that fluorescing part to emit the photons. The second technique is to put a filter in that's going to knock that off. So that will just basically take this and reduce it all down so that you get less in the band that you don't care about. So that's kind of the trick on how these are made over here. Now, when you get these, the amount of light you get is dependent upon the amount of current. More current, more light. The problem is, and that'd be perfect as long as we were in a perfect universe, but we're not in a perfect universe. So in a non-perfect universe, too much current and you burn these out. So, this, I'll be honest, I built a circuit just to give myself a test thing. And, in accidentally, my eyesight's not quite as great. I've stuck some of the LEDs in the wrong power line hole because I'm using my 9-volt batteries. And it is really easy to burn these out. I've probably burned out like 4 or 5 LEDs by accidentally sticking them in. Therefore, I acquired for myself, and if you ever get older, these are very, very helpful. What are called jeweler's loops. So I don't have them on my glasses now. I'm just kind of showing you. They're basically 2 individual lenses. You clip them on the side of your glasses. And for those of us who have trouble seeing things, you can kind of hook these lovely things on. And then I can slide in the lens that I care about. And now I can see basically like I used to maybe like 20 years ago. So very, very helpful little devices. or get yourself some helping hands or something of that sort. Uh, anyway, too late for some of these things, but I do have some functional ones here, and we'll take a look at what the circuit does. All right, so that's the emission of these. So for these, what we're going to do, this is the P, that's the N side. So I'm going to hook a resistor in series here, and you basically pick that based off how much you've got. I'm going to hook my 9-volt battery in, and away we go. We'll often just do a switch here, just so we can turn it off and on whenever we want. Since I'm going to be using 9 volts across here, um, I'm going to set this to be, well, it's also been on the resistors I had available to me. I picked a 680 because I'm doing a high voltage. If you were doing a lower voltage, like 3 volts or something, this is often when you see like the 220s and stuff like that. So you pick this basically to keep your current within a manageable range, say like 15 milliamps or something like that. You have to look on each individual LED to see how much light you're going to get out. That's going to vary. It'll vary within a batch too. But for the red LED, this seems to do a pretty good job. For my infrared LED, this has caused a lot of brightness. It should have been basically okay from their specs, but I'll be honest, since COVID and everything, acquiring my infrared ones, I had to get them from a cheap distributor quickly, and they've either been too bright or dim, so I've been having some challenges with those because I just got cheap ones, sorry. But COVID has caused all of us a little bit of problems. But this is the basic idea, and we will do this essential circuit, as simple as that is, for both sides. Now, if I was making a commercial application, right, this one I'm just kind of approximating, and if my 9-volt battery starts draining and stuff like that, it's gonna cause me to get less and less efficiency on what's happening. What I would do in a commercial application would be I would actually set up a current driver. So you can set up an op amp circuit that you can adjust the current so it drives a constant amount of current, and that constant amount of current is adjusted to however much you need for that light. Op amps are small when you put them on surface mount stuff, so this is a pretty efficient thing, and that will make sure that you don't either over or under drive your circuits, and therefore you don't burn things out as much. But since we only need it for a quick demo here, this is plenty good for what we need. It'll do the trick for us. All right. So let me check so far. Is everybody clear on how we can build this and why we build the circuit we build? Okay, I'm getting lots of yeses, so that's good. And again, if you want to check your current through here, this is kind of trivial. Essentially, assume this is a 0.7 drop, so you just get 9 volts minus 0.7 volts, which is about what you lose going through the diode. And you take that divided by 680, and that'll give you, roughly speaking, the current that's traveling through. If you get at least 10 milliamps, you probably will get light. Usually somewhere in the mid 20s, you start to look at burnout. So you can adjust accordingly. All right. On the other side, there's a couple ways. Well, actually, there's like a ton of ways you can do a photo amplification circuit. So we'll talk about a little bit here, and then we're going to build a very simple one because it'll work good enough for us. So the first and simplest way you can do it, but which I'm not going to do, I can take this and I've got my plus, minus. I can just take this and hook it across into an op amp and have my output. And usually we have a feedback resistor. I did not leave myself much room. We can do a feedback resistor hooked in. Typically, this is very large, so we get a decent amplification on it, say somewhere around a meg. And um, this type of thing, this tends to be a very precise circuit because what we're essentially doing, if you cause current to flow here, um, it's going to basically amplify your circuit and out you go. Now, that's great for precision. It's not very good for speed, though. Um, so this does not tend to um, have as good of a time properties, and that's actually more of a concern to us. We do want a fast reacting circuit because we care about the time varying amounts. And for us, the precision, you kind of lost it all because we don't know the materials. So we're going to just take the AC difference and the DC, and we'll actually figure out what our circuit actual value is from taking and adjusting that. So uh, this circuit, while it's neat, you'll see it in a lot of places, is not the best for us. What we're going to do here is we're going to take this and we'll hook this to ground on the positive side of our op amp. And on this side, we're going to hook it to our -9 volts. And basically what I'm trying to do, remember, if it's more positive on this side that I'm driving, that's a classic emitter thing. That's called forward bias. By putting a negative here, this is ground, that forces this to be ground. So this is ground, so I'm in reverse bias, and I'm reverse bias 9 volts. Now, when you have something in reverse bias, remember, you're really turning this off hard. So when it's turned off hard, that means essentially no currents flowing. You've stopped any dark currents. You just block this thing, right? Well, there's always dark currents. I shouldn't say that, but you've clamped everything down really hard. There's very little going on. And what's going to happen then, if I get any light received on this, that electron will instantly register a current, and that current is going to drive. Once this gets even a little bit open, it'll start yanking this end down hard. Right? So if I get current flowing, this end is going to drop closer to here because the difference is going to look like that 0.9. Well, that's really low. Well, that's going to force this end because I'm in the inverting op amp position. I basically have replaced this diode for one of the resistors. That's going to yank this down hard. That's going to cause this one to slam up high. So I'll get a gigantic amplification. So that's going to give me a very, very large and very fast response. So we just want to make sure we don't set this too high in order to prevent it from just slamming into the rails and things of that sort. In this case, we won't have that big of a problem because I'm not going to get that much current hitting it. I'll probably be able to get about halfway to saturation the way this circuit is kind of set up on mine. At least, experience so far, it'll get me, depending on the LED, anywhere around up to about maybe 5 volt difference, something of that sort. But that's really easy to read. So I'm not going to need much after this. Now, if I was trying to get a very sensitive thing and remove noise, like I said, a commercial version, I would then take this and you'll notice there'll be some drift that as the signal goes, it's going to kind of go up and down. So often to get the AC very cleanly, we'll pass the AC value, we'll go through a high pass filter. Now, I'm making a very careful distinction there because if you do that, you lose the DC value. So you have to have something else that's measuring your DC value. It's pretty easy on that one to just run it into a circuit that just averages things. So you just get a DC value out of it, and then you run it into a very clean high pass system. You can get the waveform very nicely, and you can use that to measure your AC value. In any case, I'm not going to worry about that because I don't need it. If you also get too many spikes, and you'll notice I do get spikes on mine, but it shouldn't cause us any problem reading the values out. If it was a problem reading the values out, then you could put a low pass filter on the other end, giving me a band pass. Very typically, the range is chosen to be about 0.5 for the low end and about 5 to maybe 10 volts or sorry, hertz for the high end. So you get a band pass filter where in the frequency domain, your cutoff is going to be somewhere around 0.5 hertz. And on the high end, the cutoff is, say, 5 hertz or a little bit more. Right? It's usually plenty good enough to get your signal out. Um, but like I said, we're not going to have a problem seeing this, so I'm not going to worry about it. All right. So really, that's actually my circuit as far as I'm going to be concerned on. I'm going to have a single receiver. I'll have two different emitters. Hopefully, that last thing I did didn't blow up my infrared one. Um, we'll see. Um, but let's at least just see this. The basic circuit idea makes sense to people. Okay, I'm seeing yeses. Okay, so when we go to build this, I'm going to use our good old friend, the LM354. If you remember, the pinout of the LM354 has basically dual op amps. So when we look at the pins, this is minus, plus, and the output, and then minus, plus, and the output. And this is your power rail, right? I should say the positive end of the power, and this is the negative rail. I call this the positive rail. So that's the basic setup of our chip. So we'll set pin 4 and pin 8 to be hooked onto our power. And then I only actually need one of these for my area. So my positive end here, move these inside just so I don't lose them. I'm going to hook this to ground. I'm going to hook from my output. I'll hook that 1 meg resistor. And then I'm going to hook my photo detector, which again, just remember a photo detector is essentially just a diode, but it's been optimized to receive photons. And now I'm going to hook this to minus 9 volts. Now, a few things for kind of setting these up, and then we'll see how I'm able to get them. So I already mentioned the important parts with the glasses, not to blow stuff up. I'm going to show something that I've found to help a lot too. A cutout piece of a toilet paper roll. So I've been using this kind of as a trick for a while to build these things because remember, you don't want any light that's going to pass through your hand. Um, the, most frequencies don't go all the way in, but from any light bulb, and I have a light source here, there's going to be red and there will be some infrared within it. There's infrared because you can feel heat on the bulb. So the more heat you feel on the bulb, the more infrared you're getting. So to block those off, I just took an old toilet paper roll, which evidently is like everybody's favorite thing now in COVID. And I just took that and some masking tape, and I taped it small enough so once I put my LEDs in, I could fit my pinky in so that it fits somewhat comfortably. I'm not going to say it's super comfortable. If I really had time, I'd kind of make a nicer thing on it. On the one that's the actual photo detector, I also took a very thin strip of paper. I measured how wide the LED was on the sides, and then a little bit past, and I cut a strip maybe like 6 inches long. I just wrapped it around a whole ton and then taped it. So you can see this kind of very thick little whitish blob. Inside that is the photo detector. So it stops any light from the side coming in. So that blocks a lot of noise that's going in. And then, I don't know, it's probably too hard to see. It's open on the top. So that when I stick my finger in on top of that, I put the soft side on top of that, and I can basically block it off completely. So any light is having to pass through my finger, essentially. That is way more opaque than my finger is because I've got like, probably 15, 20 rolls of a sheet of paper on there. And then I did a few other things. So I on my masking tape, when I put these in, I put a red mark on the outside of them so that, and I'll show you here, and then I'll have to get my things. The longer the leads is the positive lead. We'll see if I can do this. Ooh, I got it back in. Um, Most of the time I've been needing to get that jeweler's one to get on. Now, to get them through the wall of that, I actually took these. These are tweezers, but they're really sharp. And I just kind of got them to the width of these two. And from the inside, it's kind of important. If you do it from the outside, it's still a pain. From the inside, I took it and I just pushed it through the outer wall. So I ended up with two nice holes, and then I threaded them through, and then I hooked them up on these wires so that I had a setup. And then I painted, or actually, this is just a red Expo marker. I just marked on this side which one was the red LED versus the opposite side is the infrared. Um, and it's small and tight in there. I've been able to fit them in. It is kind of a pain when I have to swap them out when I have burned one of these out in the past. Um, but the advantage of blocking all the side light and giving me a way of controlling it is really, really a huge advantage. Let's see, other stuff that's useful in here. So I have also hooked up, sorry, having to grab stuff. Not the easiest demonstration thing. So I've got our oscilloscope, and we'll talk about how to set this. Um, so I have used just this kind of standard Y joint here because it's a lot easier for me to be able to hook up and connect to. The imprecision on the probe end is not as matters because, like I said, I'm going to calibrate it later because we don't know what's going on anyway. So a little bit of error doesn't matter. So when you turn one of these on, we're going to do a few things. First off, um, my voltage area, I'm anticipating I'll probably get somewhere between 1 to 2 volts total. And I want that across the entire range. So I want to see ground, and I want to be able to get all the way up to, say, like 1.8 volts, maybe if I'm lucky, somewhere around there. So let's see, how many divisions do I have? 4, 8, 8 or 9, it looks like. So I'm going to go off the presumption. I at least want one on either side. So I'm going to pick like 7 or so on here. So somewhere around, I might be able to go with 0.2 volts. So I'm going to set my channel A 0.2 volts. And then I'm going to take this. There's a couple settings here. So number one, there's an AC DC choice here. I'm going to set that to DC. Oops, too slow. So I set it to DC because otherwise it'll screen out the DC component. Remember, I need that for calibration. So that should handle that one. I need the, oh, here it is. So there's also the post value. Remember, that's the offset. I'm gonna move this whole thing down low because I want to use the whole screen. I won't have any negative components on this because everything's just absorbed. So I'm only measuring absorption, so there won't be a problem. So I've set it down really low, so that'll give me the whole screen to be able to show my wave. Um, I'm only using one channel because I've only got one detector. You switch between them. So I'm going to come in, and on my second channel, I'm just going to disable it. I don't have something in the way. There we go. All right. For my time base, I'm going to set my time base to around 0.2 seconds. Um, Again, it looks like I've got maybe 10 across here. So they give me about 2 seconds of time. Um, Being older and a little bit overweight, I would guess my heartbeat's going to be somewhere between 80 to 100. If I was older and thin, I'd guess I'd be somewhere around 70. So I guess I'm probably about 90 when I'm not doing something. I'm also, in a small little room and it's hot and sweaty in here, so that'll probably make it even higher too, because it definitely feels a little uncomfortable. Um, Anyway, so zero point 0.2 seconds should give me two, maybe three pulses on here. Um, and then for my trigger, because now I've got a very, very fast setting. And remember, we had trouble with some of the delays on this. I'm going to switch my mode to scan, which gives me a much faster mode for reading things. So anyway, that's kind of the setup on this. I can't turn this off or I will lose all that. Now I will our kind of next thing, right? I've got my 680 ohm resistor, a 1 mega ohm resistor, and I have one of our boards and on a nice backing. Thank you very much, Patrick, for the wood backings that you cut. And I've just kind of taped some 9-volt batteries on because since I'm doing this at home and I'm gonna sit in a chair while I wire these up. Well, now I'm standing, which is even more awkward. I don't want to be holding the batteries. Um, so that's kind of my setup. I've hooked this green wire you can see across because I want to have that same basic setup for the amplifier. You can see I've got, I probably should do it this way. Um, the blue wire down here is going to be my -9. The red and the blue in the middle, they're hooked together by green. So green is often used for ground. I could have used black for common, but I didn't have enough black wires, honestly. But green for ground is a fine reference for zero anyway. So I kind of use that one just to remind myself. I use dark blue for my negative, again, because I was having trouble finding the wires. And then I hooked red for my plus 9-volt wire coming in. So probably hard to see here, but I'll show my finger catches on this side. So you can tell that's where the notch is. On the other side, it just slides easily. So that one is not, there's no notch there. So the notch is on that side. So if you're looking at, this is the chip. So the -9 is going into my negative rail and my plus is going into the positive. And so then plus is actually for this. Make sure it's clear. This is my positive input and my negative input. All right. I'm now going to set up my glasses because now I really do need this. I don't like setting it on too long because they're heavy, so it pulls them down on my face a little bit. But really hard to see without this. So I am taking my my 1 meg, and the first thing I'm doing Okay. If you can see, I've now hooked it across. Actually, I guess I did on that side. Let me move it over just so I'm the same. I'll say now I've got my 1 meg hooked between the output and the minus rail. You can hopefully see that. Now I'm going to hook my plus to ground. I'm going to use a green wire for that just again for consistency's sake. You can see that, well, hopefully you can see. Might be able to get better light by putting on my phone's light here. You can hopefully see here that I've hooked the green wire across from the positive rail to the middle. You can see it's kind of, see if I can, hopefully that's visible. You can see the green wire is hooked from the positive to the middle one, which is my ground reference. And then I've got, of course, the negative hooked here. And you can see the 1 mega ohm resistor from output to the negative side. So what I'm going to want to do is take my diode, and you can see my blue is the red, which is the positive. That's this side. So I want the blue one to go to -9, and because I got a blue and a green wire on this, and the green is going to go to the minus input. And remember, the minus input's at ground, so that's actually why I did this, because it just makes it easier for me to figure out which one I'm doing. Okay, so I want to go from -9, and then I'll hook this to, well, I left for this lovely excursion, which would make it a lot easier to hook up, but I didn't. I only grabbed one. So I'm going to take my 680, and I'm going to pull that from my positive side to the 680, which will then go to the P side of this. And I'm actually put my switch in between here just because it gives me a nice gap. Then I can take, let's see, the red on this is the orange and yellow, and the orange one is the P side. Okay, so my P side is going to be orange, and yellow is going to be coming back around to give me to my negative. So I've hooked up the orange one to the other side of the switch, and the yellow one I have hooked to -9 volts. So really, I kind of did my, oh, there's my black pen. Okay. I put my switch here, which isn't pretty on my, I had to draw it out somewhere. Isn't pretty necessarily on this diagram, but it makes it much easier when I'm wiring it. And realize it doesn't matter where I cut the circuit. Cut the circuit, no current flows. My highly advanced secondary. Now, I've noticed I've been getting too much current, and that's what my fear is for the infrared, that I might have just burned it out. So I got a second 680. see, I have it in now. The other side of that 6A, I'm going to hook here, and that'll just let me plug in for the other one. And the other one, the infrared, is the red. The positive one is red, and the other one. Negative side goes to my green, my ground reference, and the output I hook here. Now, if I did everything right, I push this button. Okay, got a little bit of flicker here. Auto pull down. One more thing to reset. All right. I think I got that hook back in. So hopefully push, red light. So that means that indeed my red light is functioning. So whenever I push this button down now, we should be able to see that. So I'm going to attempt to get this into a not completely awkward spot. Not a lot of room in here, sorry. I set that here. Put, oops. Okay. All right, so hopefully you can see right now. I do have a little bit, you can actually see a small amount of some oscillations in there. I've basically got this really bright light seen above it, which is not a good thing to do. So give me 1 sec while I try to turn my phone off with one hand. Stop that. Okay, there we go. All right. And now you see it's a lot smoother. It basically takes a while to settle on this circuit. Remember I was mentioning that capacitance that's in there and create that lag. But overarching, I don't care that much. All right. You can see there's a little bit of a ripple, but I'm not too worried about it. I do not have enough hands here. Okay, I think that switch was not my best choice. Actually, let me punk my switch and just hook straight across. I'm going to do the red so you can see it. And because I'm also confident that I didn't burn that one. All right. So you can see my red light is on. My finger's a little bit fat for this, so I'm trying to get in here. Come on. Okay. Right now I'm not getting a very strong signal because every time I keep moving, my finger, it's kind of hard to see, keeps knocking the LED sideways. I'm trying to, this is a lot easier when I could do this on my table. And I might have to switch rooms here in a sec if I can't get this. Come on. Like every now and then I can get to sit just right here. Come on. Uh, Trying to squeeze this so that my finger is fits within here. Come on. Okay. Sorry, it's taking a little bit for me to get my finger adjusted in here. You can see I'm getting a much cleaner signal as I try to get my finger in here right. But when I move it around, it gets, so it's a very sensitive setup, unfortunately. And a lot of this is just my big fat fingers. Come on. Every time I move this for you to be able to see, it kind of, my finger knocks it out of position, which is very, very frustrating. See if I can snap a picture and maybe pull it back up from reference. So I've got the scan button set up here. So if I can catch this right. Okay, off the top of my screen, I have to adjust my channel value. Millions of things I don't want to try to do with my finger. All right. Last time I got a better job with it. Sorry, my right hand's a little better at holding itself still. When I use both hands to hold this, I get a beautiful signal. But then I can't click the dumb thing. Okay, I'm going to try to. My finger is not in this. You're not scanning nicely. There you go. You can kind of see it. This is awkward to hold. I'm not going to do it too long, but you can see. Okay, that's about as much as I can do without going. Was everybody able to at least see it working? As much as awkward a toilet paper roll is nowhere near as good as a hard plastic print, but you could at least see the idea, hopefully. Could everybody see it, that awkward balancing? Okay. So at least we were able to get that part visible for a sec. I'll get this laid down and borrow one of my kids and snap a picture on this, and I'll upload it so you'll have something you can measure on it. This is obviously the red channel. You could just see it here. But just given the awkwardness of trying to do this, I'm not going to try the other channel. So I'll snap a picture for you to see. And then I have to switch rapidly back and forth between the two. What I might actually do is just take one set of data for red, try to keep myself as even as possible, and take a second set of data, line them up in MATLAB, and then send those out to you so that you'll have a full set that you can measure and do a comparison. So for this lab, unfortunately, since you can't build your own, you at least saw it built. We talked about the circuit. You saw me assemble the circuit. You saw the joyous awkwardness with bare wires. I discovered right here when I was kind of twisting my hand, part of the reason I was getting a lot of noise, you can probably see they get really close here. I think it actually crossed a couple times. Again, if I was doing this, I would actually do small circuit boards on each side, and I would do surface mount LEDs because then I don't have to worry about the stupid wiring problem. Um, but that's kind of beyond the easy scope of doing it here inside. But you also saw how you had to set the O-scope up to measure it. So remember, you have to do DC value. You can't do AC. Um, and then basically the only difference to a regular pulse oximeter besides kind of a nicer surface mount instead of a toilet paper roll would be to actually have it so you turn the basic sequence kind of goes like this. I'm going to erase this so you can see the timing sequence. So you'll turn the red on and then both off. I'm going to do off for both of them off. And then you'll do the infrared and then you'll do off and then you'll repeat. And typically what people will do is they'll actually measure on the red and off and infrared, and that's just a wait state. And the reason why you measure the off is because remember I said all the light coming in from the sides? That light still goes through my finger into the detector. If you measure it when both of these are off, you've got a measure of how much light is coming in the sides. And so you can just subtract that off. You kind of filter it, so you smooth it. You find out what the kind of a constant value is, assuming that light's not changing too much. And hopefully the person's staying still because they have to get a good measure anyway. That's the other problem. As you move, you adjust the blood flow. So when I got my best measurements, I was sitting in a chair, nice and relaxed and calm, and I was getting these beautiful big waves, even better than the ones you saw, but those were still pretty good once I balanced my finger right. Um, you know, and part of what I was trying to adjust here, you can see looking in. Hopefully, let me turn this down a little. Um, hoping you can see this. If you move these wires, the LED faces different directions. If it's pointing at the photo detector, I get a really strong signal. If it moves away, it screws things up. So trying to keep my hand in there so I could get a steady reading is wasn't the easiest thing to do. Anyway, but that's the pattern that goes on. So red off, infrared. In our case, I looked at it the side light, at least when I was sitting in my chair and I turn off the lights in the room to measure it. I don't get a lot of side light, so I'm pretty good. And the toilet paper roll, at least since it's all the way around, does a reasonably good job with the lights off measuring things. All right, so that hopefully gives you everything you'll need. I'll send you the data. I'll show you a photo. You've got the theory from last time. You've got the build from this time. I have been contacted by some people who said they want to build their own, and I am totally cool with that. You've now at least seen a build that you could do. So that gets you kind of started up. If you want to do that, more than happy for you to do that. It is not a requirement though. So you can then just kind of write up your lab. And so that'll count as the homework part essentially for the photo detector. Just make sure you explain the mathematical theory of it and you give the physical theory in your lab write up. And I'll try to send you a photo of my setup here so that you'll have that for it. And I'll send you a picture of the waveform, at least one of them that I measured. And I will also send you, the data for red and infrared. I'll probably have to send you just a MATLAB file because I can't measure them at the same time. I have to switch between them. And so to put them together, I'll just put them together in MATLAB and send you the file. And then you can analyze it using one of the methods. So you should explain, here's the math method we're going to do to analyze it. And here's your oxygen value that you got. Depending on it, I mean, I'm in a small room, so my oxygen level actually, since I've been breathing and sweating in here, is probably not quite as high, just because I'm also breathing back my own breath and things of that sort. But I would get, I mean, typically people are 96 to 100. Probably not. I'm most of the time I've measured myself with a pulse ox. It's been somewhere around like, 99, something like that. Um, so I would imagine at this moment I'm probably somewhere in there. I'll send you data from a regular room though where I'm resting, so that you have as good a data. So you should be getting, I would imagine, a pulse rate somewhere between mid 80s to mid 90s, something like that. And you should probably get oxygenation pretty close from sitting in a chair, 98, 99%. Um, and I might do, if I get time, I might do a couple different breathing patterns because if you breathe really fast, you'll pump your heart up. And it's kind of cool to see that on a pulse ox. But we'll see if I have time, and it's kind of awkward to do that. So if I can borrow one of my kids, I'll get that for you. All right. Hopefully that gives you enough information for the lab, and you understand how the circuit's built and everything else. Is there any questions?
You said that op amp was an LM354?
358.
358, okay.
It's the same one we used before. The 358 is one of those kind of lovely old standbys. It's a low voltage one, so it's really good to use. If I was going to take this and say read it into like an Arduino or a Raspberry Pi, it's nice. It operates well off of battery voltages. Um, the 741 is another great op amp. It's got a lot more flexibility, but it needs more power. So 358 is pretty easily available, and it's cheap and it's low power.
All right. Is the lab report similar to the previous ones we've done for this lab?
Yeah. You're just going to pretend what I'm sending you on the circuit is what you sent, because it's just not feasible for everybody to get all this stuff.
Okay.
So each person will kind of do their own. And like I said, I'll upload the data and I'll put it on the linked page, so you'll have photos and everything else. Um, so what I'm really getting out of from this lab report is that you can write up the sections. You're going to have a thing explain the math. You'll have a brief explanation of the physics. Um, you'll have an explanation of the circuit, and you'll have an explanation of how you calculated both my heart rate and my blood oxygenation level. Um, and you already know what I'm looking for value wise. So that's just a good way to check yourself sanity. But you should see that value calculated out. And since I know that, I'm more going to be looking to make sure that you use the equation correct and put the right values in. Does that make sense?
Yes.
Awesome. Any other questions? Does anybody have questions in the rest of the class?
A question about the final reports about the final project.
Yeah.
I remembered as well. Um, so we have to choose a novel device that's not FDA approved, but to find a similar one and then explain it. Is that correct?
Um, for practicality speak, since you have to include data, um, my modification was pick something that you can, that's, an FDA device that you can, that's simple enough that you can give an explanation for. If you want to make kind of like what I'm going to a pseudo novel, like let's say you got an Apple iPhone, with the measurement. I think that's what I used as or an the iWatch or whatever. Or I don't care. Android probably has its version too. Um, Whatever it is that where they're measuring the pulse ox values. So, you could talk about that and say, hey, look, I'm building an app that's going to measure oxygenation routinely and feed it. Now, there's probably somebody who does that already. That's a pretty obvious application. But pick something like that where you can kind of explain it. But you're not going to have time to build it, and I don't have equipment for you to be able to build it. That's where you're at. So my modification of that is picking something you can find enough data to fill in your report.
So it will be better to be like an actual FDA approved device.
Um, well, I don't think an iWatch is an technically if
Right.
they won't get you approved, but you know it. The approved, you have to go through the whole PMA pre-market approval process, which is for simple type of stuff. It's not. So just pick something that's a reasonable device that has already gone through the either the 510K process or is a simple device that would be able to get in easy data. So I guess one more example that might be a helpful one. Um, uh, what is it? Branson's space group. I forget which one he has. Virgin Space. He has some name for the because he owns Virgin Atlantic and. But anyway, his group just made a ventilator that can be easily and rapidly deployed for um, use now in the COVID situation. Or maybe you're going to do some type of an LED system that uses ultraviolet LEDs because we know ultraviolet light kills the coronavirus. Kills a lot of viruses actually. So that's one of the purifiers used is ultraviolet light because it'll damage their RNA and that'll kill them off. Um, so maybe you're doing a mask sterilizer using ultraviolet light, and maybe you're going to look at reflectance to see, how much reflectance. Maybe the cleanliness is based upon, what that reflectance value is. I don't know that for certain. That's kind of a guess, but I would imagine it's potentially possible. Um, so you'll pick something like that enough where you can kind of get some data from looking online. There are a lot of ultraviolet cleaners, so you could get data on that. Um, the Branson thing, I've read a few articles on his stuff, and there's some other groups that are doing it too. Branson was working with, I think it was UC Berkeley and UT Austin on his, and there's a couple other groups that are out there that are building these kind of easy to fabricate ventilators. You'd be welcome to take and kind of write up on one of those. Imagine you were the person on that team who was going to apply for, the FDA to allow you to use this device. That'd be another option that's going in. Um, and there is a special, actually, if you're interested, there's a special application process during an emergency. What's called a humanitarian crisis. So you can apply for a very fast approval for use of something if the normal, slow, rigorous approval would cause people to die, basically. It doesn't give you long term, but it at least says, hey, look, you can, this is at least considered safe enough to use for an emergency or humanitarian crisis.
Another question is like you mentioned the data. So if a device like you mentioned Branson's device group, the device is not manufactured or widely used yet. They don't have the device, but do we choose a similar device to gather the data of another ventilator and then to imply that?
Yeah, I'm not as concerned as you know, whether this is the most accurate data in the universe, quality wise, even if you kind of hand sketched it. What I would care about the data is this that you present data that is going to actually do what you're trying to accomplish here, which remember, the goal is to prove that your new device is as safe as and as reliable as. So I don't care at the moment. Normally, I would care that you actually were measuring it precisely, but um, right now, I just care that you show that it's reasonable data. So if you got, let's say you're going to compare your ventilator to another ventilator, and you got some statistics from that ventilator, and you found that, what matters is maybe the frequency of the breathing and the volume displacement and, you know, some statistical data on. You pick out what were the key things. And you can find this by doing the 510K searches. If you remember, we did that a couple months ago. We looked through the 510K database. you can actually pull up information on a bunch of those to show, what is the key things. You get the product, you can find out what was the important data they do, and then you say, hey, I've got to look like that. So as far as I'm concerned, you can, at that point, once you've shown me accurate data from the device you're comparing to, you can fake the data for your own. And I don't care if you fake the data by finding some data. I don't care if you sketch it. Just note, this is fake data because we can't actually, because we don't want to ever look like we're lying on these things. But I understand you can't build it to test it. So as long as you note, this is artificially produced data, on the picture itself, then you can just kind of pretend that you had good data for the paper. Because what I care about the second part, so number one is showing that you know what you need to compare to. And number two is that you're walking through a process where you would explain your device, how it would work, how you would build it, and what would be necessary if you were going through that 510K process. This is actually, like I said, it's a shortened version of what you would actually do for the cover section of this, the summary part of a 510K. Does that help?
Yes, yes, thank you.
Awesome. Any other questions? Okay, so I'm contemplating this, at least other than the awkwardness of it, seems to work fairly well for things. And I do think the question and answer part is helpful. So my intention at the moment, if everybody's good with it, is on Thursday just to do another one of these. Is that okay with everybody else?
Sure.
So that way, if you've got questions or whatever you need on, there's not a lot past this. We're going to do an EEG coming up, and if I have time, I tried to grab one of the thermometers, the digital chip ones. I'll have to hook it up to like a Raspberry Pi or something to read it out, because most of the ones that I've bought use a protocol to transmit their signals. So you need another computer on the other end to read it. I do have a Raspberry Pi, so if I get a chance, I'll program that up and share that. Because the only thing that I remember we have left is EEG and the thermometer, and then just time for all of you to ask questions for your final project stuff. So I think time-wise, we're looking pretty good as long as everybody's got an idea for their projects. All right, well, if there's no other questions, then I will say goodbye. So one last call. Any questions? Nope. All right, well, have a great day, everybody. Look for a link on for this Thursday.
Have a good day.
You too.
Thank you for your time.